Welcome. In this video I give you a quick and dirty introduction into limits. Now limits will be a very central object in the calculus class, and we will have several videos discussing limits. This is one of the first ones, and so I do it a little bit more informal to help you understand what's going on. So we write limit as x goes to a, f of x equals L. And what we mean by this is we let x go to a, very, very closely to a, but maybe unequal to a. And then the function f of x approaches a value called L. We say the limit of f of x as x approaches a equals L if we can make the value of f arbitrarily close to L by taking x sufficiently close to a. So here arbitrarily close means as close as we want. And sufficiently close to a means close to a from either side. That's important. We have to do it from values which are bigger than a, but also from values which are less than a, but not equal to a. So that's what's going on in this definition. Let's look at an example. So here is the function x squared minus 1 divided by x minus 1. And we look at the limit as x goes to 1. Of course, we see immediately that this is a mean question, right? So if I write f of x is x squared minus 1 divided by x minus 1, and if I look at the domain, right, then the value x is equal to 1 is not in the domain. We are not allowed to substitute x is equal to 1. So the domain would in this case be minus infinity to 1, excluded, and then union 1 to infinity, meaning we can use any number but 1. And then, of course, this is exactly the limit I'm asking you or I'm asking myself to compute. So the limit x to 1 of x squared minus 1 divided by x minus 1. Let's look at this for the two cases when x is less than 1 and when x is bigger than 1. And I just do this procedure as explained in the previous slide by letting x getting closer and closer to 1 and computing the value of the function f. Here will be the value x, and here is x squared minus 1 divided by x minus 1. So for example, if I start lower than 1, I could start with 0. If I sub in 0, I get 1. If I sub in 0.25, I get 1.25. I prepared these calculations. You can easily do it on a calculator, and you will see you will get the same numbers. If I put 0.5, I get 1.5. So here on the left, I'm getting closer and closer to the limit value, which is 1. So let's try 0.99. Then here I get 1.99. Oh, so you might get an idea what's happening. Do one more step. So 0.999. Then I get 1.999. So it really looks like it will approach 2. Okay, so here we get an idea. Maybe this approaches 2. And I give it a question mark because this is not a mathematical proof, it is just a hint or a hunch. So let's try values which are bigger than 1 here on the other side. So for example, 2 is a value bigger than 1. If I sub in the value 2, I get 3. If I sub in 1.75, then here I get 2.75. If I sub in 1.5, I get 2.5. And so on and so on. So I want to approach the value 1 from above. So then here I try 1.01 or 1.001. And what do I get? I get 2.01 here, 2.001 here. Very clearly, I approximate the value of 2. Okay, so we have a good candidate that this limit L is actually equal to 2. But how can we be sure? I mean, we could play this game further and go to 0.999999999999999, and we get 1.9999999. Okay, you get the drift. We can actually do this mathematically, and let me do that on the next slide. So in this example, it is actually useful to transform the function f. We have f is x squared minus 1 divided by x minus 1. The numerator is the difference of squares. So we can write this as x minus 1 times x plus 1 divided by x minus 1. As long as x is not equal to 1. Okay, so 1 has to be excluded also from this calculation. Nevertheless, if x is not equal to 1, we can actually cancel a common factor, all right, and we get x plus 1. So the function f is in fact the function x plus 1 for the case that x is not equal to 1 and undefined if x is equal to 1. So this is our function f. Plotted it on the next slide. Unfortunately, my writing will disappear, so I have to rewrite it again. Here we go. So it is a linear function x plus 1 with the exception of this one dot sitting at 1 and 2. So here it is undefined. Now we were looking at the limit. At the limit as x approaches 1, which is the undefined point, from the left or from the right, and we would like to know what the limit of the function is. So graphically we are interested in these limits, which I indicate through the arrows. As x gets closer and closer to 1, the function gets closer and closer to 2. We can write limit x to 1, x squared minus 1 divided by x minus 1. And here we can do the same trick as before, because in the limit x is actually not equal to 1. So we can write x minus 1, x plus 1 divided by x minus 1. We cancel the common factor, then this is limit as x goes to 1 of the function x plus 1. But now I can take the limit. This new function x plus 1 is actually defined, so in that case I can actually take the limit. This is 1 plus 1, which is equal to 2, and this is what we guessed anyways. Although the function is not defined at 1, the limit is. So that's all already for limits. So this is a new notation we have to get used to. X goes to a, then f of x goes to L, if this is possible, if the limit exists. And there are many examples where it doesn't. There are other examples where L is plus or minus infinity. We still say the limit does not exist. And there are examples where the limit does exist and we get a finite number L. Hey! Hey Tolo, what are you doing? You are getting as close to the limit as you can? Bzzz. Oh, Tolo.